Hi everyone, I'm Shri. Today I'm going to give a glimpse of what it takes to run these FSD networks in the car and how do we optimize for the inference latency. Today I'm going to focus just on the FSD lanes network that John just talked about. So when we started this track, we wanted to know if we can run this FSD lanes network natively on the TRIP engine, which is our in-house neural network accelerator that we built in the FSD computer. When we built this hardware, we kept it simple, and we made sure it can do one thing ridiculously fast: dense dot products. But this architecture is autoregressive and iterative, where it crunches through multiple attention blocks in the inner loop, producing sparse points directly at every step. So the challenge here was, how can we do this sparse point prediction and sparse computation on a dense dot product engine? Let's see how we did this on the TRIP. So the network predicts the heat map of most probable spatial locations of the point. Now we do a argmax and a one-hot operation, which gives the one-hot encoding of the index of the spatial location. Now we need to select the embedding associated with this index from an embedding table that is learned during training. To do this on TRIP, we actually built a lookup table in SRAM, and we engineered the dimensions of this embedding such that we could achieve all of this thing with just matrix multiplication. Not just that, we also wanted to store this embedding into a token cache so that we don't recompute this for every iteration, rather reuse it for future point prediction. Again, we pulled some tricks here where we did all these operations just on the dot product engine. It's actually cool that our team found creative ways to map all these operations on the TRIP engine in ways that were not even imagined when this hardware was designed. But that's not the only thing we had to do to make this work. We actually implemented a whole lot of operations and features to make this model compilable, to improve the int8 accuracy, as well as to optimize performance. All of these things helped us run this 75 million parameter model just under 10 milliseconds of latency, consuming just 8 watts of power. But this is not the only architecture running in the car. There are so many other architectures, modules, and networks we need to run in the car. To give a sense of scale, there are about a billion parameters of all the networks combined, producing around 1,000 neural network signals. So we need to make sure we optimize them jointly and such that we maximize the compute utilization, throughput, and minimize the latency. So we built a compiler just for neural networks that shares the structure to traditional compilers. As you can see, it takes the massive graph of neural nets with 150K nodes and 375K connection, takes this thing, partitions them into independent subgraphs, and compiles each of those subgraphs natively for the inference devices. Then we have a neural network linker, which shares the structure to traditional linker, where we perform this link time optimization. There we solve an offline optimization problem with compute memory and memory bandwidth constraints, so that it comes with an optimized schedule that gets executed in the car. On the runtime, we designed a hybrid scheduling system which basically does heterogeneous scheduling on one SoC and distributed scheduling across both the SoCs to run these networks in a model parallel fashion. To get 100 TOPS of compute utilization, we need to optimize across all the layers of software, right from tuning the network architecture, the compiler, all the way to implementing a low latency, high bandwidth RDMA link across both the SoCs, and in fact, going even deeper to understanding and optimizing the cache coherent and non-coherent data paths of the accelerator in the SoC. This is a lot of optimization at every level in order to make sure we get the highest frame rate, and as every millisecond counts here. And this is just the visualization of the neural networks that are running in the car. This is our digital brain, essentially. As you can see, these operations are nothing but just the matrix multiplication, convolution, to name a few, real operations running in the car. To train this network with a billion parameters, you need a lot of labeled data. So Egan is going to talk about how do we achieve this with the auto labeling pipeline?